All right, are you all keen? Because there is a rover landing on Mars in less than 24 hours. Unless you're watching this video after the rover's already landed or crashed into the surface, and in which case this video has aged horribly. But anyway, let's see at what the mission of the Perseverance rover looks like. I wanted to do a little bit of a video because most of the content out there has been kind of lower quality than what I was hoping for. There's a lot of cool Australian connections with this Mars rover mission, and that's something I want to talk a little bit about as well. So, first off, let me show you guys just how much stuff we can analyze just using the satellite data that NOAA and NASA have made available. So starting off with this true color image of the Earth here. And I said I wanted to mention the Australian links to Mars. And if you look at Australia from space, there should be one thing standing out to you when you compare it to the rest of the Earth's surface. Now, this is a true color image, and it should be blaringly obvious that we are red as heck when you compare us to the rest of the world, right? Now, why is that? Well, let's zoom in on that a little bit. Let's see what we look like. Woo, go Australia. Now, this is an image that was taken in the November last year where there were fires on the East Coast. So it shows you some of the other cool things that you can see with this satellite data. But certainly, in the middle of Australia, in the outback, we've got a whole bunch of this red color. Now, this red is actually the same mineral that causes the surface of Mars to be strongly red. It's iron oxide, right? Which is the color that iron goes when it rusts. So we have some really iron-rich soils in the Australian outback, and it's what's given us the red color. Now, this unique geology of Australia has given the Australian geologists an edge with analyzing these types of rocks. Also, our continental crust is way older than the rest of the continental crust on Earth. So the Australian rocks are some of the oldest in the world. Pretty much, they've just been there getting slowly weathered and rusted into this red color. And that's why the oldest evidence of life has actually been found in the Pilbara region, around here somewhere, in Western Australia. So this is why there were two scientists, Abigail Orwood and David Flannery, that are playing a big role in this Mars mission, because they're pretty much the experts on analyzing and what it takes to find ancient life on Earth. And so, you know, you're going to get people who are good at finding ancient life on Earth to look for ancient life on Mars. So that's a little bit about the Australian connection there. And by the way, with this sort of data, you can get all sorts of other overlays if you want to. So any teachers out there that want to bring satellite imagery into the classroom, let me see, how do we get that? Yeah, here you go. You can click on all sorts of different things here and overlay pretty much whatever you want to. All this great data. This is all on the NOAA website, so it's pretty great. Totally underutilized for space science, but yeah, I think the Earth true color image is by far the coolest. You can view up to, what's that, like, you know, yesterday or 2 days ago. So yeah, all of this data is available pretty much soon after it's taken. All right, so let's head on over to Mars then. Now, this is a different website. This is Mars Trek, which is also another great one. It's pretty similar. It's just Mars instead of Earth. You can change between a globe and a flat sort of global map. So I kind of like the globe for now. Let's make it back into the globe. Now, that red color, we know what that is because we were just chatting about that with Australia. It's the iron oxide, right? The same thing that makes Uluru red is the mineral that makes the surface of Mars very red. And these rocks are incredibly old, just like the rocks in the Australian outback. But there are some other colors that you should notice on Mars, right? We see a whole bunch of black all over the surface. And of course, you've noticed the white up there at the North Pole, down here in a massive crater, a massive basin, and in the South Pole. So the white should be obvious. That's ice, right? Just like we have ice at the North Pole and the South Pole on Earth. Now, this is mostly water ice. There are also seasonal ice caps of dry ice, carbon dioxide ice that sort of grow and then retreat. But actually, a lot of people mistakenly say these ice caps, oh, yeah, that's dry ice. No, it's not. It's actually large majority water ice. So that could be an important resource for, future Mars missions. Now, the black color, that is actually from igneous rocks, from basalt primarily, that's been spread all across the surface of Mars through past volcanism. So there's got to be some source of this, some sort of evidence that there was volcanism in the past other than these black rocks. And this is where we see it here, right? So when we're looking at this satellite imagery, if you're a teacher, you can do this sort of activity with your students where you guide them through looking at the colors, right? Because the colors of a planet can tell us a lot about it. You can then also guide them through looking at surface features. So here, what sort of surface features are we noticing? Well, we see these massive mountains, right? These massive mountains. This one's actually the largest mountain in the solar system here, Olympus Mons. Right in the middle of it, this thing called a caldera. A caldera is where the lava chamber of the volcano has sort of cooled down and collapsed in on itself, like dipped in. So this is showing us that there were volcanoes in the past on Mars, which is aligning with our observation of the black basalt rocks that we see spewed out all over the surface. So cool. So just by looking at the colors and the surface features, we can see there's volcanoes on Mars. Whoa, what about this thing over here? Now, this is super interesting. By the way, with these volcanoes, they're not active anymore, and we will get to that as to why they're not active anymore. So this is another amazing surface feature that we see on Mars. This massive canyon, Valles Marineris, the largest by volume canyon in the solar system, I believe. Not the deepest, right? The deepest canyon is right here on Earth, but the largest by volume. So largest combination of depth, width, and length. All right. Now, this is particularly interesting. You see all these weird features around here. Now, if you're not used to interpreting as much data as you can from these sorts of satellite imagery, you might just think, oh yeah, okay, that's a cool canyon. But what we should be thinking is, what do we see with canyons on Earth? And can we see any evidence of stuff like that on Mars? So, comparing this to the Grand Canyon on Earth, what do you see going through the Grand Canyon on Earth? You've got the Colorado River, right? So we've got to look around here and see, is there any evidence that there might have been water flowing through this feature, through this valley in the past? So, do you see anything around there that looks like it might be formed by water flowing through or eroding through the surface of Mars? This is actually one of the best places on Mars to look for that. So this is another great challenge. If you are a teacher doing this sort of activity with your students, you get them to see if they can spot an area that looks like it might be an ancient river flowing on the surface of Mars. And so they might point at this region up here where you can see massive amounts of erosion down here. This would be the sort of point where I would then switch from like the globe just to the normal map, because the map really stands out here. And you can also zoom in much closer and see much more detail. So there are some very, very detailed images for some parts of Mars here. It's just amazing. Like exploring, you could have fun exploring this sort of stuff all day. Give the students in your class each a different location that they've got to analyze the colors, the surface features. And by the way, you can even analyze the elevation, which is pretty fun to do up here. So you could, you can calculate elevation, draw a line, and you can sort of pick any spot that you want to. I'm going to draw a line across there, and then it will make an elevation profile where you can see how deep that ancient river actually went. Here, negative 3,000 meters, so about 3-kilometer deep lake, we think, running through there. That gives you an idea of just how massive this must have been. So yeah, these are really great tools to use in the classroom, but also if you're just a nerd and just want to geek out with exploring Mars, man, you can have a fun afternoon just like drawing elevation profiles all over the surface and seeing this sort of data. It's amazing that we have this data just all freely accessible online for Mars. So you can see all of these sorts of ancient looking rivers here. Really, really cool. And down here, certainly as well, coming out of the Marineris Valley. So they do think that there was water flowing through or forming part of the erosion that was in this Marineris Valley, yeah, at some point in the past. Now, of course, where there's rivers, there's got to be something else, right? Like, rivers don't just flow into nothing, do they? Let's see where all these rivers seem to be flowing. Up into this northern area up here. In fact, we can even see it up there. We can see all sorts of river-like structures, right, that all seem to be flowing into this northern region. Now, if we analyze another surface feature on Mars, which is the distribution of craters, then you can see there's a massive density of craters in this sort of general southern highlands area of Mars. I say this is the highlands because it's all elevated compared to the rest of Mars, which we'll see when we look at the topography in a second, right? Now compare the crater density here, or if we go into the globe mode, the crater density when you're looking at it from the South Pole, massive number of craters, compared to when you're looking at Mars from the North Pole. Sure, there's a few craters, but really not many. And this is another part of the hint that's telling us that we think that there used to be an ocean covering this half of Mars. So let's go to our rivers down here. Here we go. So we think that these rivers, these ancient riverbeds, were flowing into a massive northern ocean up here. And that's left behind, now that the ocean's not there anymore, left behind all this sort of sandy terrain, these dunes. And it's much younger terrain, so it's much younger than the southern highlands area, because you can use the craters actually to tell you a little bit about the age. All right, the older that the surface of a planet is, the more craters you would expect it to have there. And so this southern part's much older and much more aged than the northern part, which we think is younger. It's more dune-like sort of terrain. And craters don't stick around very long in that sort of terrain as well. So it could be a combination of it being a younger geological surface, but also that the craters get wiped away from the winds blowing the dunes around. Just like if the oceans evaporated on Earth, right? What would you expect the terrain to look like at the part that was the ocean floor? You're not going to expect it to be really solid, hard rocks. You're going to expect it to be sandy sort of dunes. And craters will not last for long in that sort of environment. So craters are really, really useful analysis tool as well for telling us about the age and the history of a planet. Now, that's pretty much the limits of what we can get to just looking at this sort of data, the colors and the surface features. If you want to go further, you've got to go to something like this, which is where we get all of the topography data. So the elevation profiles of Mars. This is all from the Mars Orbiter Laser Altimeter. So you can use this website. I'll put all these websites in the description below, by the way. So you could download this one. It's a massive image file. You zoom in on different parts of it, and you can see what it looks like on the surface. So this really makes the elevation stand out. You can see that all of these rivers here definitely look like they're flowing into this massive northern ocean. The blue is showing us low terrain, right? So the whole northern hemisphere of Mars is about 4 kilometers lower than the southern highlands, right? We've got a massive crater down in the southern highlands, but if you ignore that, the rest of it's just absolutely way higher. Way more craters as well. And this further really accentuates that. So this is pretty conclusive that there used to be something here. Now, there have been theories that that this was a massive glacier or a massive ice sheet and not oceans. But the predominant view is still that this was a massive northern ocean.
if we zoom in on certain parts on the full scale map, then you can really see those rivers that we were looking at before. They look pretty cool when you're looking at them with the topography map. And it makes it much more obvious that there was water flowing through these areas in the past. So just a quick mention on the alternative theory. If you did want to check that out, this was just released last year, and I don't know, I'm not sold on it. Like this is the map that they produced, where they said they analyzed all of these different ancient riverbeds and said whether they thought it was due to subglacial meltwater flowing or surface runoff, which would be normal rivers. And like all of the popular like science like reported this as, oh, we found out that Mars didn't have oceans, it just had ice. But really, if you look at all of the red patches, which is just normal surface runoff, just normal rivers, they found that quite a lot of the places that they observed were just caused by surface water. So it was by no means a study that showed that there was no surface water and it was all ice. And even these parts that say subglacial, what that means is that like there's just a thin layer or a thick layer maybe of ice on the top, and then you've still got water down at the bottom. So that's still somewhere where life could be, right? So yeah, I guess jury's still out whether it was like predominantly icy or an ocean. Well, who knows? Maybe through different geological time periods, both environments existed. But that's still like a developing thing. We're not quite exactly sure on that. So back to the topography. One of the things that this is telling us is that if we want to search for life on Mars, we should be searching in these sorts of environments, right? If you want to search for life on Mars, probably not the best to be sending something down to the southern highlands, right? This is where it's at, up in the northern lowlands. And you probably want to go in one of these sort of like coastal sort of areas, right? Where there would be an ancient dry riverbed. This is just where you're more likely to find life if it was on Earth, right? So where are we going to be sending the Mars rover? Well, we're going to be sending it to this zone here. I believe one of these craters here. We'll find it on the normal map, but it is one of these craters here, which is right on the side of an ancient lake bed. So one of these is the Jezreel Crater, and we'll go back and we'll look at that in the high resolution images and see why it is that the Jezreel Crater is so exciting. But this is a zone that's right on the transition between the southern highlands and the northern lowlands, and that's where you want to be looking for life. So this is the first Martian mission that's really been focused on an area that is somewhere basically like along this line and where they, you know, have a decent chance of finding evidence of life. So just on this, further evidence that the northern lowlands are much more recent geologically can be found in the magnetic field. This is showing the polarity of the magnetic field remnants that are measured on Mars, right? There is no magnetic field anymore, but there are some remnants from the crust. Basically, the crust has been magnetized by the ancient core that was magnetic, or that did have a dipole, and that has been lost. That dynamo effect's been lost in the core, but some of the remnant old rocks still have that magnetic field. So what we can see here is consistent with what we've seen with the other data that we've analyzed, which is that this northern area is much more recent geologically, and there's been much more going on there. Basically, this area here would probably be potentially one of the most boring places that you could send like a rover to land on Mars, because the rock's been doing pretty much nothing there for the history of Mars. Like the surface has just been getting hit by craters, and that's pretty much it. All right. But who knows? Maybe if you wanted to really get an idea into the really early history of Mars, then you might want to land something there. But it's pretty cool that the magnetic field data aligns with what we see with all of the other satellite imagery and everything. Now, I should mention that this by itself as well, there's still like all of this data has to be interpreted in combination with everything else. So this is indicating that the northern part is much younger, but there's also been studies that have been done where they found a whole bunch of buried craters. All right, so they use radar basically sounding like through the ground, like to echo back and to detect craters that are buried underneath the surface of Mars. And using this technique, they found a whole bunch of craters. Pretty much every spot that they analyze, they find these buried craters. And this is in the northern lowlands region, the area that we say is very young. So is it true that it's very young? Or is it that it's old, but it's covered in young sand and dust and dunes on top? Could be either. So, yeah, there's a lot of stuff still to learn about this, but pretty much these are the regions that they analyzed with this technique. These little white patches here, and all of the black spots are buried craters that they found in these regions. So you can see they found, out of the places that they looked, they found quite a fair few buried craters, right? Like just in this spot here. So that's telling us that the northern lowlands might be older than the data that we're looking at is suggesting. It might just be a young sand dune-like surface coating a thin layer on top of an ancient, old, cratered, harder, rocky surface, like what we've got down here. But that's just more, fun to think about, but not really useful. So, we'll get to that later. So let's go back to the topography and check out, here we go, back to Mars Trek. Let's check out the Jezreel zone. So Mars Trek is awesome. If you look up Jezreel, what do we want to find? Perseverance 2020 landing site. And we're going to go we're going to go to the normal global map for this. So you can just search up here for anything that you want to on Mars. Then you can add it and it'll add that zone and it flies you to it. Yay. So here we are. We're at some really nice zoomed in images basically. All right. So if I'm just zooming out to show you where we are, this is the lake that I was talking about before that the Jezreel Crater is on the side of. We're going to zoom in on that and see why is it that we're landing there. So I'm going to push that off to the side. All right. Now, this is really fun. Different areas on Mars that you zoom on will have this high resolution imagery. Some areas won't. Now, the most obvious thing that you should be looking for is signs of water or water erosion, more like it over here, because obviously there's no water here anymore. And you can see what looks like an ancient river flowing through here, all right? And then flowing out this side as well. And of course, we can calculate the elevation profile on that, which is pretty cool. So, you could do the elevation across the entire lake or crater-like lake and just see, wow, just how deep it goes. You could also go over, we could do the elevation just over this region here to see what the depth of the river going into it might have looked like. So, just analyzing that feature and making sure, yeah, that definitely is a river. And also, what about this river delta here? This is an area that the scientists are very interested in. So, let's, oops, what did I get there? Did I draw that one across properly? Let me draw it across again. Okay, that's interesting. Seems to have that picture behind it. Well, let's pick that sort of area there. And yeah, okay, I guess that doesn't really seem to be telling us that much interesting stuff because this picture is overlaid over the top. You can't really see the line, which is a bit frustrating. But let's zoom in on that delta region. This is an area that is going to be of main interest. Like, this is where the Perseverance rover is going to be driving around basically in this delta. And it's going to be hoping to find some sort of evidence of life. And this rock here is sedimentary rock in this river delta. So basically just layers and layers of rock that's been brought down from the river and sort of settled there. And could give us a bit of a insight into the history of if there was any life in this lake. But it also seems like the perfect environment, at least in the view of the Australian scientists that discovered the old life in outback Australia, they said this seems like a pretty good environment to be searching for microbial fossilized remnants of life. Now, what would that look like? Well, I have a piece of it here. Let me just turn my camera back on. So what they're hoping to find is something that looks kind of like this. Now, this is a slice of the Strelley Pool stromatolite. That's the oldest fossilized life on Earth. You can see all of the layers going through it. Looks kind of like a lasagna, just with layers of like rock and we've got the polished side there. We've got the unpolished side there, which also shows more the true color. Now, just looking at this rock is not enough to say that it is ancient life. All right? Like, sure, it looks great, but what Abigail had to do, she had to prove that this was not formed by abiotic means, right? So that it wasn't just a natural rock formation. She had to prove that this was formed by life. And the way that you've got to do that is you've got to use basically an X-ray microscope, I think. So X-ray microscope, and they basically look at the traces of organic matter in minerals on the microscopic scale in this fossil. So what they do when they find that is, yes, if there's elevated levels of things that are organic or suggesting the presence of organics, then that stromatolite, well, it's a stromatolite. It's fossilized bacteria. It's not just a normal, sedimentary rock that's formed in this special way that might mimic the look of bacteria. All right. So will they find that in this area here? Who knows? But it seems like a pretty good place to look. And it's pretty awesome that it's going to be Australian scientists that have designed, well, it's an Australian scientist that's designed this, Abigail, and it's going to be Australian scientists that are involved in analyzing this data. So her and collaborators in Brisbane. So that's David Flannery, which is going to be involved with that as well. So that's pretty cool. And, it brings us back to, when we're looking at Earth, brings us back to Australia in that really the environment that they're searching is an environment they hope will have similar sort of potential for having old life as the Australian outback does in its rocks. Now, what's one of the first things that they're going to do if they find life on Mars? Well, there is this interesting theory called Panspermia, and that's what I want to finish on. All right, so before I go on, I want to show you guys this. This is a Martian meteorite. So how do we know it's from Mars? You analyze the isotope data from it, and you see that it doesn't match the isotope fingerprint for Earth. And because we have rovers on Mars, it was actually the Curiosity rover that gave us the final data for what the Martian isotopes should resemble. And we can match rocks that land on Earth to Mars if they match the isotope data that the Curiosity rover sent back to us. Now, this would have been a much bigger rock, obviously, and it's just been sliced up like a loaf of bread. But you can buy slices of Mars, all right? It's not cheap, but you can buy a slice of Mars. Where they find these, this one was found in the Sahara Desert. Of course, doesn't mean that all the Martian meteorites land in the Sahara Desert, but it's a good place to look because if you find a rock on top of the sand in the Sahara Desert, it's very likely that it came from space. There's not many other places it could have come. But you'd expect that there'd be an equal amount of Martian meteorites landing all over the Earth. It's just that you find them in the places where it's easiest to look. You're not going to expect to find Martian meteorites in the middle of the Amazon jungle. There's just too much stuff in the way, right? But they would be in there. They'd be in there. There's maybe a caterpillar crawling across one right now. It doesn't have an idea that it's crawling across a piece of Mars. So that is cool. We've got bits of Mars that land on Earth. And the cool thing about this is that this has been happening for a really long time. Like, we were obviously getting hit by more objects in the past because Mars was getting, we were getting hit by more pieces of Mars in the past because Mars was getting hit by
more junk from space. So all of the craters that were formed on Mars, basically the maximum bombardment by meteorites was in the early history of the solar system. And so plenty of Mars would have been transferred to Earth. And it's even thought that possibly, well, no, it's thought that it's pretty likely that bits of Earth have been transferred to Mars too. Now, because Mars's gravity is weaker, it's much easier for a piece of Mars to get to Earth than for a piece of Earth to get to Mars, right? Because Earth has to overcome greater gravity when it's hit by a crater for bits to be shot out. But like the collision that happened 65 million years ago that contributed to taking out the dinosaurs, it's likely that would have spewed bits of Earth all over the solar system onto different places, onto the moon, onto Mars, onto Venus maybe. So this is happening. This theory of panspermia, of material being transferred between planets, and the potential that life could hitchhike on this material. Now, this is exciting because if we find evidence of life on Mars, it could be one of two things, right? It could be a new genesis of life. It could be completely unrelated to any life on Earth. Or it could actually be related to life on Earth. And so that's one of the first questions they'll be asking if they do find life on Mars. Now, they might not find any life at all, but, if they do, it'll be pretty interesting. I don't know which one I would prefer, whether it's the second genesis or related to life on Earth. I think second genesis would be cooler because it tells us that if we have a second genesis of life on Mars, then life must just be everywhere in the universe because, that's only 2 planets that we've analyzed, sample size of 2, and we find it on both planets, then it must just be everywhere. But, it could be interesting either way. And if there has been life formed on one planet and transferred to another, it's more likely that it started on Mars. The reason why it's more likely that it started on Mars is because the Martian surface cooled. It cooled much faster than the Earth's surface did early on when the planets had formed. And so oceans formed on Mars before they formed on Earth. The reason being Mars is much smaller and just small objects cool down faster. That's why Mars unfortunately lost its magnetic field. And that was a big turning point for Mars, right? So it's more likely that the oceans were around on Mars for, a billion or so years, giving the potential for life to evolve, and that they might have been transferred, that life might have been transferred on a Martian meteorite to somewhere on Earth in that time. So I'll put all the links for all this sort of stuff down in the description. Look, this is just me sharing stuff that I've just learned just for fun, but I think it'd be great stuff for kids in the classroom. Or, maybe just a parent, if you've just got a nerdy kid that's into this sort of space stuff, then, get them on Mars Trek and have them explore around. It's awesome stuff. Like, they won't get bored. You can literally look up all of these, different things. You can search for whatever you want to on Mars. Like, you can go search for where all the different landing sites are. And yeah, there's a lot of really cool things you can do with this satellite data. And it's just fun. If you haven't had a go on Mars Trek, you should have a go. So yeah, awesome. All right, thanks for joining me then, guys. And yeah, I hope that you learned something new from this video. And oh man, fingers crossed that this rover does not blow up tomorrow, all right? Fingers crossed.